Alright, this paper may very well be one of the landmark paper for the world of large language model. This paper investigates the ability of language models to create and manipulate mental images in their mind's eye for spatial reasoning task, that is, having the character of space, drawing inspiration from human cognitive mechanism. The authors propose the visualization of thought or VOT prompting method, which augments LLMs with a visual-spatial sketchpad to visualize their reasoning steps and inform subsequent steps. Now, VOT adopts zero-shot prompting instead of relying on few-shot demonstration or text-to-image visualization with the clip. So let me explain first the concept of mind's eye for spatial reasoning in simple terms. Let's consider the example of navigating through a city using a map. Imagine you are visiting a new city and need to find your way from your hotel to a popular tourist attraction. You have a physical map with you, which you study carefully before starting your journey. And as you examine the map, you create a mental image of the route in your mind's eye. You visualize the streets, landmarks, and turns you will need to take to reach your destination. This mental image acts as a visuospatial sketchpad, allowing you to mentally simulate the navigation process. So while navigating, you refer to your mental image to guide your decisions. At each intersection, you mentally check your progress against the visualized route, ensuring you are on the right path. If you encounter an obstacle or need to make a detour, you can mentally manipulate the image to find an alternative route. And throughout the navigation process, you continuously update and refine your mental image based on your actual experience and any new information you gather along the way. This dynamic interaction between your mental visualization and the real-world feedback helps you make informed decisions and successfully reach your destination. In this example, the mind's eye plays a crucial role in spatial reasoning by allowing you to create, manipulate, and update mental representation of the spatial environment. It enables you to plan, simulate, and adapt your navigation strategy based on the visualized information. Similarly, the visualization of thought or VOT prompting technique aims to equip large language models with an analogous capability. By prompting LLMs to generate visualizations of their reasoning steps, VOT enables them to create and manipulate mental images of the problem space, guiding their decision-making process and enhancing their spatial reasoning abilities. To evaluate the effectiveness of VOT in spatial reasoning, the author selected 3 tasks that require spatial awareness in large language models, which are natural language navigation, visual navigation, and visual tiling. These tasks were designed to test the understanding of space, direction, and geometric shape reasoning. And the paper does experimentations comparing the two main models, that is the regular GPT-4 and GPT-4v, and prompting techniques across the 3 tasks. And the results show that VOT prompting consistently induces large language models to visualize their reasoning steps and inform subsequent steps, leading to a significant performance improvement. And also, qualitative analysis reveals that GPT-4 VOT exhibits visual state tracking behaviors, generating visualizations of intermediate reasoning states before the final answer. This tracking rate is significantly higher compared to the regular GPT-4 chain of thought without explicit visualization prompts. The visualizations enhances the final answer by grounding the reasoning and reducing hallucinations. However, performance of GPT-4 VOT is still far from perfect, especially in the most challenging route planning task, because despite the task being relatively easy for humans, large language model performance drops significantly as task complexity increases. Inconsistencies between language and visualizations are also commonly observed in this paper. And here is a statement from the paper. GPT-4 VOT significantly outperforms other settings in all tasks across all metrics. The significant gap when comparing GPT-4 VOT with GPT-4 COT, that is a chain of thought, and GPT-4 without visualization demonstrates the effectiveness of visual state tracking, which allows large language models visually interpret their actions within an grounded world. And in the natural language navigation task, GPT-4 VOT outperforms GPT-4 without visualization by 27%. And this table shows the actual numbers, and obviously GPT-4 VOT is the highest performing one in this table. And earlier I said that for the evaluation of the VOT, they chose three different techniques: natural language navigation, visual navigation, and visual tiling. So here in this part taken from the paper, that's what it is shown. So the natural language navigation involves navigating a space based on verbal instruction and recognizing previously visited location. This task tests the model's ability to understand spatial structures and loop closures. And for the second method, that is visual navigation, this challenges the model to navigate a 2D, that is two-dimensional grid world using visual cues, generating instruction for movement and route planning. This task assesses the model's ability to visually interpret space and predict subsequent movement. And the third technique, that is visual tiling, it involves giving the task to the model with arranging various shaped tiles within a confined area, enhancing its spatial reasoning regarding geometry and spatial fit. And the accuracy in spatial reasoning task for large language model is measured by matching the model's outputs against ground truths using substring matching. For route planning task, navigation instructions are normalized by executing each instruction and ignoring those that violate navigation rules. And the effectiveness of route planning is assessed through the completing rate, which is a ratio of the length of the normalized instruction sequence to the total ground truth instructions. Two matrices are used to evaluate performance, which is the average completing rate across all instruction sequences and the success rate, which indicates the proportion of sequences where the model successfully navigates to the destination. And indeed, GPT-4 VOT, that is visual prompting technique, shows a significant improvement over configurations without visualization, such as GPT-4V chain of thought and GPT-4V without visualization, with a notable 27% better performance in natural language navigation task. This suggests that incorporating visualizations help language models better interpret actions within a grounded context. But additionally, I would also need to state that VOT prompting might not be as effective in tasks that can be solved through logical reasoning without visual aids. In experiments involving natural language navigation within a ring, where instructions involve simple mathematical calculations, GPT-4 using chain of thought prompting without visualizations outperformed VOT, suggesting that in some context, straightforward logical reasoning may be more efficient than visual reasoning.